I was just telling somebody, when Ronald Reagan was testing the mic during the Olympics, he didn't know it was connected throughout the world. He said, check, check, let us mute the Russians. I was just telling somebody, when Ronald Reagan was testing the mic during the Olympics, he didn't know it was connected throughout the world. He said, check, check, let us mute the Russians.
Check mic check.
Good afternoon, everyone. Hello.
इसको तो नहीं हो ओके नहीं म्यूट कर दिया म्यूट कर उसमें होगा हाँ ये तो है म्यूट ओके
Hello. Hello. It's okay.
Yeah.
Okay, so now we can start. So, good afternoon, everyone. After this intense photo shoot, now welcome back. And
I know the shoot was not with a revolver, but a camera.
yeah, so welcome to this colloquium. And today we are happy to have Professor T.R. Seshadri with us for this colloquium as a speaker. So Professor Seshadri holds an integrated MS from IIT Delhi and a PhD in theoretical astrophysics from TIFR. With extensive research experience at various institutes across the globe, including, let's say, PRL, CSIR, and University of Sussex in UK. He has served as a faculty member at HRI, and then he joined the current institute, Department of Physics and Astrophysics, University of Delhi. Now he's serving as a professor there. His impactful work explores various topics, starting from cosmic microwave background radiations, cosmic magnetic fields, dark energy, and atmospheric aerosols. And these are reflected in his publications, which is more than 55. Presently, he is focused on the thermodynamics of cloud formations. So basically bridging the gaps between atmospheric science and astrophysics. So while doing so, he is also actively teaching and various courses.
I was afraid what he is talking
about. So now we'll hear from him directly, the universe, which is currently visible to us, universe today, and his experience and his
Not my
research.
experience. Okay.
His research. Okay, welcome.
Thanks a lot. Thanks a lot for the kind introduction. A measure of how old you are is how long the introduction is, because you have been doing various things. Okay. So today, thanks a lot. It's a very nice friends. I already gave the talk yesterday. So today I will wear a different hat. Today I wear the cosmology hat. So what I will be talking today is a kind of a khichdi of various things in the universe, starting from the beginning and the state of the universe today. And in course of this description, I will be focusing on what we understand, what we do not understand, what we think we understand, and what we pretend to understand. So let us start with the birth of the universe. What do we know about the birth of the universe? Answer is simple, honestly nothing. And the reason is the following. See, what is the problem with this? You see, if you take relativity, you have the speed of light c, which characterizes relativity. You have gravity, which is g, and you have quantum physics, which has h cross. Together with all these things, you can generate the following dimensional objects, namely time scale, which is Planck time, which is 10 to the power minus 44 seconds, Planck length, which is 10 to the power minus 33 centimeters, and Planck energy, which is 10 to the power 19 GeV. Now, what we are interested today is the first one. Necessarily, the birth of the universe means it is deep inside the Planck era. It is before 10 to the power minus 44 seconds. So, since all these things are involved, it is clear that we need a theory of quantum gravity if we actually want to understand the birth of the universe. We do not know how to quantize gravity. And that is precisely why we cannot describe with any degree of confidence what is the birth of the universe. In fact, there is this quantum gravitationist called Karel Kuhash. He made a very interesting statement at one stage. He said, while giving a talk on quantum gravity, he said, while a lot of interesting work has been done in last 2 decades, nothing which can be called progress has been achieved during this time. So, no, that is the status of quantum gravity. So let us say, the moment you can't do anything, you start jumping to something which you can do something about. So let us go to a time scale of greater than 10 to the power minus 36 seconds. Then we just about begin to understand what may be happening in the universe. Around 10 to the power minus 36 seconds, the universe is believed to have expanded by a huge amount, by a factor of 10 to the power plus 28 in a duration of a time span of 10 to the power minus 34 seconds. And this, okay, the numbers as to know exactly how much duration, exactly what factor can differ from model to model, but by and large, it is sort of agreed that there has been this vast expansion within a short time, which is termed inflation. Yeah, universe expanded by a factor of 10 to the power 28, magnified, yeah. Okay. What is the mechanism to produce inflation? Well, here, I mean, one will not say one does not know, but one will at the same time say we don't know for sure, because there are several models and several suggestions to produce this. There is symmetry breaking, modification of gravity, etc., etc., etc. But when we do not know how inflation was produced, why do we believe that inflation actually happened? And that is because without inflation, certain observed features did not have an explanation. And I will focus on three particular problems in non-inflationary models. The first one is called why is the space flat? Now let me just explain. Remember, I am not saying why is the space-time flat. Space-time is not flat. I'm talking about why is the space flat. So it is like, if suppose you have a two-dimensional, suppose we live in a world which is two spatial dimensions and one time dimension, okay? And we have a two-dimensional insect, in this space. So you could have a homogeneous space, which is the surface of a sphere, and the insect is on this one, and it sees the spatial section as curved. Or the insect could be living on a flat rubber sheet, where it is not curved. Now, if by experiments the insect finds that any experiment it does, it always is consistent with a flat space, the insect will ask the following question: what is the physical mechanism by which nature chose the spatial sections of the universe to be flat and not curved? Now, without inflation, this does not have any satisfactory answer. There is no satisfactory answer as to why the universe has spatially flat sections. What it means is, if at a particular time I freeze everything, then Euclidean geometry will describe everything. Okay? Why is it so? Okay. Now, inflation, I will come to the details, but inflation hides the non-flatness by making it nearly flat. And when I have put that hides in red, it's one purpose. Because it doesn't solve the problem, it actually hides it, as I will just elaborate. The other thing which you see is that the universe is homogeneous and isotropic. Okay? Now, if suppose you go to a city and you find that everybody is speaking one particular language. You go to another place in the world and they find they speak the same language. So a whole set of places, they are speaking the same language. Now, it cannot be that by sheer coincidence, everybody is speaking the same language. This means all of them must have some common source because of which they are affected. So similarly, if suppose the universe is homogeneous and isotropic, it means all regions of the universe should have been causally connected by some common source which could have led it to a homogeneity and isotropy. The problem in non-inflationary universe is that there is no way in which you can make the universe as one causally connected patch. And the question arises, then why is it that the universe is homogeneous? Once again, inflation honestly does not solve the problem, it hides the problem. And I will again explain why is it so. The problem which actually inflation solves is what I call the mystery behind the generation of structures in a homogeneous universe. And this is where inflation gives you a mechanism to produce this using quantum principles. And I will tell you why using quantum principle is not a matter of choice, but is necessary for producing perturbations in a homogeneous universe. So inflation provides a mechanism to explain these, or at least to hide the problem. The issue of flatness. So as I said, it is observed that spatial section. I think even this mic can't tolerate my volume of the voice. Okay. 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 So the question is, why are all observations are consistent with the spatial sections being flat? So, or why is the universe flat? When I say universe is flat, I mean spatially flat, not space-time flat. The ideal solution will be to try to discover a symmetry which mandates such a situation. That is, you have a symmetry under which you say that if the symmetry is violated, the universe may not be flat. And since nature preserves the symmetry, the universe is flat. That is very ideal solution which you would like to have. Does inflation provide such a solution of fundamental nature? The answer is no. Then what does it do? What inflation does is to evolve the universe to a stage in such a way that the non-flatness is below the detectability level. And that is exactly what I mean by hiding the problem. So, again, it doesn't make the universe flat at a fundamental level. It is something like the insect asks, why is it that my space is nearly flat? I say, I expand this sphere so huge radius that in local experiment, it doesn't know whether it is flat or curved. It is that kind of a solution. Okay. So inflation does this. The next problem is why the universe is homogeneous, and this requires a bit more explanation, as is clear from this view graph. So on the y-axis, I have plotted not exactly time, but what I call conformal time. Forget about the term conformal time, but it is something related to time. Okay, and on the horizontal, I have taken x and y axis, and here I have taken the example of, as before, a universe which is 2 plus 1 dimensional, 2 spatial and 1 time dimension. Now, this is today's epoch, and today I am seeing the universe from a backward light cone. Okay, so I have drawn a light cone here, and then, okay, this I will come to shortly, but most of you must be knowing there is something called microwave background from where we are receiving light, which is at a redshift of 1000. So that is this surface. Now, what we see is that when the universe was at a redshift of 1000, by which means the universe was a factor of 1000 smaller than what it is today, the universe is perfectly homogeneous. Okay. Now, suppose we consider the beginning of the universe, or nearly the beginning of the universe. Now, different points will start affecting different regions within a light cone. So, like for example, this point will affect this region, this point will affect this region, and so on. But one thing is that none of the points can affect a pink region of another cone. Then it would require light to travel faster than c. Okay, which means that this region, this surface, is actually consists of several causally disconnected regions which could have never talked to each other. The question now arises, when I see this circle which passes through all these disks, why is it that all points of the circle are alike? That is the homogeneity and isotropy. Although they are passing through different disks, with none of which could have communicated with each other, why is it so similar? This is the horizon problem, homogeneity problem. And so here, for example, this is called the surface of last scatter. In a realistic 3 plus 1 dimensional universe, instead of a surface of last scatter, the circle of last scatter, I will see a spherical surface of last scatter, and I will see patches. I should see patches of causally disconnected regions, and the question arises why they are all similar. And again, inflation solves it, rather hides it in an interesting manner. What inflation does is, I told you that inflation involves a huge expansion of the universe in the early time. Now, when you substitute in the integral of eta, what it basically does is that this portion, eta rect minus eta I, instead of being small, it increases by a large factor. As a result, this forward light cone becomes large, and each of the disks in the backward light cone is contained within one forward light cone disk. So as I said, all these pink disks are causally connected within each other, not among each other. But here, this one disk has become so big. So what I am seeing today is within one disk. So it is no surprise that the universe is homogeneous. Now the catch here is the following. This information I get from the microwave background. Tomorrow, if I am able to see the cosmic neutrino background, I will actually go to a much earlier time, and this cone will become bigger, this will become smaller, and this may reoccur. So what inflation does is, till what I have observed today, I am giving a solution. I can't guarantee tomorrow if I make more observations whether this will be valid. So that is why again I call it hides the solution. The third, which is I think is the major success of inflation, other than the fact that this was my PhD work. Okay, so that is the quantum origin of density perturbation, and this requires a bit of a description. See, if you start with an absolutely homogeneous universe, identical. Now, if you say there is a, okay, so to begin with, it is believed that today, you have all these galaxies and clusters of galaxies and everything. How did they form? What is believed is the universe initially was completely homogeneous to begin with, because initially there is no reason why one place should be different from the other place. So everything should be homogeneous. And there were small perturbations. These perturbations collapsed because of gravity and kept growing till they formed the galaxies, clusters of galaxies, etc. today. So that is it is like, Ramayana being told in one line. Okay, so this is what, but there's a catch here, and the catch is the following. If you have a completely homogeneous universe, and I have to create perturbation, what is perturbation? Perturbation means the density is no more a function purely of time, but is also a function of space. Which means at one point in space, density should be different from another point. If the universe is homogeneous and isotropic, why is it that one point should be selected and have more density than the other point? So, hence, classically, we can never actually have a theory in which, starting from a homogeneous universe, you can have inhomogeneity. So what is the solution? And like many other things, quantum mechanics comes in to a rescue. Now, you see, what quantum mechanics basically says is the following. It says, there are two things. Suppose I have a line, a number line, and I have got coins at every point. This is the difference in generation. When I say coins, in my mind, I always think of a 10 paisa coin, which probably most of you must not have even seen. Okay, okay. So I have coins kept, and they are identical coins. Then they are identical coins, and the probability of getting heads or tail is half for each of them. In this way, all these coins are identical. So in this whole number line, it's a homogeneous thing. There is no preference of one point to another. Now what I do is I toss the coin. Some will come head, some will come tail. So after it is tossed, I look at it, it is no more homogeneous. There is some that are tail, there are heads. Now there is a catch, but it started homogeneous. So what quantum mechanics says is, homogeneity is not the result, but homogeneity is what is the probability of it having some value. So the probability of it having any density is uniform everywhere. But when you actually do a realization, the actual density which you get is different. So what it first of all requires is, in order to produce inhomogeneity from a homogeneous universe, you have to bring in a process which has a probabilistic aspect. Which is the most obvious theory which has probabilistic aspect? Quantum mechanics. Okay, so let us see how it works out. Now in quantum mechanics, we have the uncertainty principle. Delta x, delta y, delta p greater than or equal to h cross beta. Now what does it mean? It means, as you know, you can't measure x and p with arbitrary accuracy. So if suppose you have a function which is a function of x and p, then either through x or through p or through both, this function necessarily will have an uncertainty. You cannot get rid of the uncertainty in f. Then you can actually do it. Okay, so you have f, df, delta f is equal to del f by del x, delta x, del f by del p, delta p. Now, since delta x, delta p both can never be 0, delta f can never be 0. Okay. It means that if you have a function of x and p, I can't make it 0. So now, what is energy density? Energy density basically have a kinetic energy density part and a potential energy density part. One is momentum square by 2. The other is, if it is simple harmonic oscillator, half kx square. So it means that the roughly p portion comes from one, x portion comes from the other, and the energy density combines both. It means because of the uncertainty principle, I can never have density which is without uncertainty. So it means that in this whole space, although the probability of density being a given number is the same, the actual value of density will have an uncertainty which, just like each coin had an uncertainty of heads or tail, which translated into somewhere head and somewhere tail, the fact that there's an uncertainty in the energy density means energy density will be some value somewhere and some other value somewhere else. And hence, an inhomogeneity. It is no more homogeneous. And hence, since density is higher in some portions and lower in some portions, you have density perturbations, which now classical gravity takes over, gravitationally collapses, and then produces the density perturbation which we see today. But there are two aspects. One is the generation of density perturbation, which I just mentioned. And then there is another interesting thing which I'll come to, which is making them super horizon size. And inflation, as I said, actually solves this problem and does not merely hide it. So as I said, first one, the problem is the generation of density perturbation. And so this is which I just told. There is another problem, which is if I actually plot length scales on the y-axis and time on the x-axis, and I take the horizon size of the universe, the horizon size will go with time something like this. Whereas if I take a perturbation and evolve it backwards with the expansion of the universe, it will actually go like this with time. What it means is, any perturbation which I have seen today, which is within the horizon, if I go sufficiently back, it is actually getting created at a scale which is bigger than the horizon, which cannot happen. Because the horizon is a maximum causally connected region. How can a physical process act coherently over scale bigger than the speed of light constant? So these two were the major problems in the standard, by which I mean non-inflationary cosmology. And as I said, in inflationary cosmology, of course, the quantum uncertainty led to the density perturbation, which I just explained. And here what happens is, because of the expansion of the universe, the horizon is always like this, but the length scale is not like this. Okay. So if this is the length scale, without inflation, it would have gone like this. But because of inflation, before some point, it actually has an exponential expansion. So what I see today within the horizon was indeed outside the horizon in the past, but if I go sufficiently further in the past during the inflationary era, it was actually within the horizon. So there is no problem in creating these perturbations over these scales. So this is how the inflationary cosmology solves this problem. So, fine. So you have done till 10 to the power minus 34 seconds. You have got this. You have got some basic thing about the universe going. What happens beyond this? What happens is, there are theories where I understand in a patchy way. And the problem is, see, for example, we expect that certain processes in early universe during this era will be related to electroweak theory, which sort of we understand well. Okay? At the same time, we also expect that there will be free quarks, because there are very high energies and the quarks need not be bounded and there can be free quarks. But then the question is, do we understand the theory of free quarks? Our understanding of free quarks is far from complete. And that is why this understanding in this region is patchy. Some features we understand and some features we don't. Now we come to 10 to the power minus 32 seconds. And from minus 32 seconds till when the universe was 300,000 years old, it is all well. I mean, so we understand fairly well. Okay. So let us start. What happens just before 10 to the power minus 2 seconds? The temperature of the universe is about 10 to the power 11 Kelvin. And the constituents of the universe are primarily protons, electrons, photons, neutrinos, and their antiparticles. Okay. Quarks have already got bound into protons and neutrons. Oh, I forgot an important thing, which is neutrons here. Okay. Okay. So the neutrinos. Okay. Now, here what happens, the energy at this stage, 10 to the power 11 Kelvin, is so high that the photon energy is much more than the rest energy of protons. As a result, of course, P plus side should be. The proton and antiproton can give 2 gamma, but the gammas have sufficient energy to produce protons and antiprotons back. As a result, there is an equilibrium which is there. Similarly, electron and positrons annihilate to form 2 gamma, but the gammas are sufficient energy in the background this, and so that it comes back. The neutrinos are interact through weak interaction. However, the densities are so large that the interaction cross-section is still large, and the neutrinos are in equilibrium with this universe. So when I say, so because of this equilibrium, the temperature of all the constituents is the same. You know, so if you have 2 objects and they are in equilibrium, thermal equilibrium, the temperature is the same. Then we go to 1/100th of a second. Previously it was just before 10 to the power 11 Kelvin. Now it is 10 to the power 11 Kelvin. Now the universe consists of a smooth soup of elementary particles. What happens is protons and antiproton, the energy has just dropped low so that protons, antiprotons can lead to 2 gamma as it always does. But the gammas no longer have sufficient energy to produce back proton and antiproton. As a result, protons and antiprotons start annihilating, and the amount of proton antiproton starts decreasing in the universe because there's only a one-way ticket now. Okay. However, since electrons are 2000 times lighter than protons, they can be produced by gamma, so they are still in equilibrium. Then we go to next step of 1/3 of that temperature, 310 to the power 10 Kelvin. The time scale is 1/10 of a second. And at this stage, you see, even if neutrons and protons, see, they are almost of the same mass. So the number densities are roughly the same. If you put it in the phase space density and calculate, number densities will be almost same. However, neutrons decay, but protons do not. As a result, neutrons are continuously reducing, whereas protons are not. So among the nucleons, at this stage, 38% of the nucleons are neutrons and 62% are protons. We take another step of divide by 3 Kelvin. The matter density now is 380,000 grams per cc. But although it's so large, the density now is not enough to keep the neutrinos in equilibrium. So they no more interact with the rest of the matter, and they are just whizzing past without any interaction. So the important thing here is, if now there is a change in the temperature of the rest of the universe, it will not be communicated to the neutrino. Neutrino will continue to be at the same temperature as it was before, because it no more interacts. And the equilibrium of electron and positron has just started shifting to the right. What happened to protons before? And in the meantime, neutrons are decaying. Now the ratio of the neutron to proton is now 24 to 76. And this number which I'm telling is just not for academic curiosity. You will land up in a very important result, which you understand. which you know, okay? You see, it has reduced to 10 to the power 10 Kelvin, but the universe still is too energetic that you can't form stable nuclei. If you form stable nuclei, the photons have enough energy to disrupt it. So let us go to one step further, which is 1/10 of a second. And temperature is 3 billion Kelvin. By now, photon temperatures have become so less that the same fate which protons and positrons met, electrons or positrons are met. Once again, this direction, the reaction goes, the reverse reaction is stopped because photons no more have enough energy to have. Photon energy is less than the rest energy of electron, so it cannot produce electrons anymore. So only this direction goes. Now the universe is cool enough to form helium and tritium, but there is a catch. You see, if you have seen a road accident, you have seen two vehicles collide. How many times have you seen three vehicles collide simultaneously? Almost never. So it is highly improbable that three things come together. So all this helium, whether it's helium-3, helium-4 or tritium, it requires more than two nucleons to come together at the same time, which is not possible. So in order to create these, you have to go through an intermediate process to have a particle with two nucleons onto which the third nucleon is added. And such a particle is a deuterium. So what you want is, first a deuterium forms, a proton and neutron, and on this there is the neutron which comes, that makes tritium, or proton which comes, which makes helium-3. So the catch is, although universe is cool enough to form helium, it is not cool enough to have deuterium in a stable form. That is, although the deuterium forms, even before another nucleon attaches to it, the photons are so energetic that they disrupt it. So it is something like, suppose you have a water tank here, and you have another water tank here. Now, if you pour water, energetically it is favorable to come to the lower one. But suppose there's a barrier. Unless it crosses the barrier, it can't come. The deuterium is like that barrier. Although energetically this is favorable, it is not able to go there because it has to go through this. This is commonly called the deuterium bottleneck. So the formation of nuclei is delayed. And the proton to neutron to proton ratio is 17:83. See, let me repeat. This happens because protons don't decay. Neutrinos actually decay with a half-life of 13 minutes. Nuclear physics. Now the universe is 3 minutes old. Now you must have guessed where I got all this from. Weinberg's book on first 3 minutes. Okay. So by now the temperature is 10 to the power 9 Kelvin. The neutron to proton is 14:86, and this is a magic number. Now tritium formation is also energetically favorable before, but the deuterium bottleneck is still there. Now just beyond this energy, 3 minutes, deuterium becomes stable. The moment deuterium becomes stable, since the other things are already energetically favorable, almost instantaneously helium and tritium get formed. All remaining neutrons, free neutrons, those 14%, get locked up in helium. And now you can do an interesting calculation, which is that if you have 100 nucleons, you have 14 neutrons and 86 protons. 14 neutrons will join up with 14 protons to give 7 helium nuclei. And the rest of the 86 minus 14 protons will give 72 hydrogen nuclei. Relative weight of helium is 28. Relative weight of the 7 nuclei helium nuclei is 78, of 72 hydrogen 78. So the relative ratio of helium to hydrogen is 28:72. And that is exactly how you understand why the ratio of cosmic abundance in the universe, the helium to hydrogen ratio by weight is 28% to 72%. This is exactly the thing which you, I mean, this I am telling because this is one thing, one of the few things I feel one completely understands in the evolution of the universe. Now, what happens from 3 minutes to 300 years? Actually, from 3 minutes to 300 years, we understand everything. And that is because almost nothing happens. Okay? I mean, if suppose you go to an exam and no question paper is given, you don't have any wrong answer. Okay? So, till it is 130,000 years old, the universe is radiation dominated. And I'm not going to details beyond this matter dominant. That's because radiation drops more steeply than matter. And so initially it's radiation dominated, goes to matter dominated. And I mean, there's some technicality as to when these are equal, there is something happens, let's forget that. But there are two important events which happens when the universe is 300,000 years old. See, as I said, the photons have a very high energy, and I also told you about its effect on the nuclear physics. But what I did not tell you till now is another important thing at what is its effect on atomic physics. The photons are so energetic that the matter in the universe, even after it forms nuclei, is in the form of plasma and not neutral matter. But when the universe is 300,000 years old, the energy of the photon is equal to the hydrogen ionization energy. And this is, I mean, this comes from the Saha equation formula, okay? Saha ionization formula. And so the moment the universe goes below this, the photons do not have enough energy to keep matter in the ionized form, and they become neutral. So this is the transition from the plasma universe to a neutral universe. It happens when the universe was about 300,000 years old. Another important thing which happens beyond 300,000 years old is that the universe undergoes an accelerated expansion, which I'll come towards the end. Yeah, so once the transition has happened from ions to atoms, now ions are charged particles. So photons can't go freely through ions, they will get scattered. But the moment it becomes atoms, the photons are no more stopped. They can just whiz past. There is nothing to absorb it. Okay? So as a result, till some point in the universe, the photons were scattered. So it is like if you try to see the universe through a fog, you will not, I mean, a building through a fog, you won't be able to get a good picture. Why? Because the photon from the building has got scattered in the fog and the information is lost. So similarly, from before 300,000 years, the photons which are traveling have got so scattered by ions that no information we are able to get from there. However, after it becomes atoms, the photons can travel freely. And so today, we are getting these photons from all directions. And these were, of course, at a temperature of 3000 Kelvin. And if that was the thing, it would have been a very good microwave oven, the universe, and we would have got microwaved. But nature is kind. As the photons are traveling from 300,000 years old, the universe is expanding and the photon energy is reducing. And today we are receiving these photons at 2.73 Kelvin, which is the cosmic microwave background radiation. And I told you about the horizon problem where those disks are seen, and this plane is that epoch. So the light which we are getting is the cosmic microwave background. So why is the universe homogeneous translates to why is the cosmic microwave background isotropic? Okay, so inflation basically says that it's all under one single domain, so it is isotropic. And so this is how the universe will look like, the cosmic microwave background. This appears very homogeneous, as it should, because that's what we said. However, I also said that the formation of galaxies involves the gravitational growth of perturbation. The moment you have gravitational growth of perturbation, it has an effect on the microwave background which is there. So today, although it is primarily isotropic, I should see small anisotropy in this primarily isotropic background. Now, before 1992, there were lots of attempts made to see the anisotropy, and it had failed, although one believed that there has to be some anisotropy if our theories of formation of galaxies there. But in 1992, the Kobe satellite actually observed the anisotropy, and that anisotropy was minuscule. 1 part in 10 to the power 5. And that is why it looks very homogeneous. If you remove the homogeneous component, this is how it will look like. Because here only the anisotropies are plotted. Wait. Oh, wait. Okay. Okay. Technology is dangerous. Okay. Sorry. This means +5. 1 part in 10 to +5. I meant 10 to the power -5 level. Yeah. Okay. So this is the cosmic microwave background radiation. And okay. So fine. So the progress in observational aspects is that this was the Kobe satellite, which saw the microwave background. 2003 WMAP, much better resolution, even better resolution Planck. Now, if you see the progress in observation, you can compare it. Suppose the same level of progress was there in observing the Earth. If this is the Earth today, this is how Kobe would have shown. Okay. I mean, there is another interesting picture, which I don't have, in which there is a baby, and it's completely blurred. You can't even make out it's a baby in the Kobe map. But if it is like a resolution of Planck, you can even see the thing written on the band here. Okay. So a tempting thought is there. And a tempting thought is, for times beyond 300,000 years, it's a low energy phenomenon. It's all below 13.6 eV, okay, hydrogen ionization. And theories of physics at this level have been validated by several experiments. So you expect that we understand, I mean, it's not comply, but completely, okay, that we understand completely the universe very well. Sadly, that is not true. And most of the problems today are actually emanating from this region where we think we understand the theory. So let me just tell one by one what are they. One is the problem of dark matter. So when you, and most people will know, but anyway, for completeness, I will mention, you have the galaxy, and when you see a spiral galaxy, the stars are going around in circle. Most of the light is concentrated in the center. So to begin with, one thinks that most of the matter is concentrated in the center. So it means just like sun has most of the matter and planets go around, since planets velocity goes as 1 by square root of r, Keplerian orbit, you expect that the velocity of stars from different distances from the center of the galaxy should go as 1 by square root of r. So if you measure this velocity by Doppler measurement, this is how you expect it should go. When the measurement was done, it was a complete surprise. Not only it was almost constant, it was actually increasing with distance. Now, this was completely out of the blue. Nobody had any explanation of how it could happen. The only explanation which could be the following, which was that here, see, if suppose in a stable circular orbit, you need larger velocity, it means v square by r is larger. So if you put gm by r squared, m has to be larger. It means there is more mass in this region than what this indicates, which means this empty region where there is no light, there is actually a lot of mass which is not emitting light, but it is gravitating. And that is what is called dark matter. So it was proposed that there is this dark matter which is responsible for producing this extra velocity. Now there are also other theories called MOND, modified Newtonian gravity, but there is an observation of a bullet cluster by which it is almost now ruled out that that is not true. So the question is, what is dark matter made of? We do not know. Okay, a lot of paper, again, a lot of papers will be there. this I always say, several times in physics, when you don't understand something and you try hard and don't understand, you give it a new name and you pretend to understand. Okay, so you call it dark matter. Okay. Then there is something which I told you earlier, is a late time accelerated cosmic expansion. Now, you see, when Einstein formulated his theory, then he was governed by aesthetics of science, and for good reason. He said that just like why should one region of the universe be preferred over the other, similarly, why should today be preferred over yesterday? So not only the universe should be homogeneous in space, it should be constant in time. So Einstein wanted a static universe. When he formulated, as a natural consequence of it, the universe was not static. But Einstein realized that he did not use a particular term, which is now called a cosmological constant, but by providing the cosmological constant, it provides effectively a repulsive term which will exactly compensate gravity, and the universe will be static. Then there is, of course, the rest of the history that Hubble found there was expanding, then Einstein dropped this and so on. But in those days, before 1998, almost anybody who has worked in cosmology, including me, has spent a part of the life trying to figure out the most natural thing is to have a non-zero cosmological constant because it is admissible in the theory of Einstein. But it is zero. Is there a fundamental reason by which we can make it zero? While this was going on in 1998, they suddenly realized from an observation of faraway supernova that it is actually non-zero. It is non-zero cosmological constant. Okay? And this cosmological constant, if you put in, then the universe can undergo an accelerated expansion. But this cosmological constant had its own theoretical problems about its origin. So the question was, how do you explain the late time acceleration? First of all, is it a problem of our understanding of gravity? Or is it a problem of our understanding of nature of matter? Or something else? We do not know. Okay? Once again, like often happens, they say it may be some strange kind of matter. What is that matter? Since I do not know, I call it dark energy. Okay. The other is the ionization history of late time universe. Now, as I said, the universe became neutral at the time of recombination, and the universe keeps cooling. Fine. So it should remain neutral. But when you made observations, what you realize that the universe, the late time universe, is not unionized, but it has a finite ionization. Now the question is, what could be the reason of this ionization? There are a variety of reasons, possibilities given to different degrees of success. But do we actually understand fully? We are not sure. There are theories which could say that it is a decay of some exotic matter. There are theories which says early star formation. And there are various possibilities, but nothing which is, complete that it can go to a textbook. Then this thing which is dear to my heart, which is the origin of magnetic fields. Okay? Now, magnetic field is something which we observe at almost all scales in the universe. And most of these can be explained by some astrophysical process, like Beerman battery, like Beerman battery or flux freezing and so on. But magnetic fields are also found in huge cosmic voids. They are huge, so huge that astrophysical methods cannot have generated a magnetic field on these scales, on these cosmological voids. Now, what we need is a process in early universe such that it generated in a small scale, and like inflation, it expands, okay, and covers the larger region. But then the point is, the moment it expands, magnetic field energy density drops as 1/4 power of the size of the universe. So it will just dilute away. So you need to have some mechanism by which you need to regenerate magnetic field at the end of inflation. And within the framework of Maxwell theory, I mean, something called conformal invariance, which I won't go to, within the framework of Maxwell theory, you cannot generate it. So what is so you need to violate Maxwell equation. What is the nature of violation and how to achieve it? We do not know. Then, I think this is the last one. Then there is something which is the issue with the value of simple as Hubble parameter. Now, the Hubble parameter can be determined by various ways. You can measure faraway galaxies, you can measure supernova and the relationship between redshift and luminosity distance, you can get Hubble parameter. You can get Hubble parameter by looking at the microwave background, because that also enters as a parameter. But the one which you measure by supernova explosion, supernovae, does not match with the Hubble parameter as seen by microwave background. And the discrepancy is well above the error bars. Okay. So the question, so again, when there's a problem, you give it a name and you feel very happy. So you call it Hubble tension. Okay. How do you explain it? We do not know. Okay. So the conclusion is the following. You see, while I will not, but there has been a lot of progress in understanding of the universe, there are some things which we think there is no reason why we should not be understanding, but we do not understand. So the strategy is three-pronged. First is new ideas are needed. And what we call out-of-the-box approach. But often theoretical physicists, I'm a theoretical physicist, but still I admit it. When you go out of the box thing in theoretical physics, you go completely berserk with no this one about whether it is observationally possible or not. So one should make sure that whatever theory you're doing, there is some observational signature by which you can get some idea. The other is better in experiments, which includes instruments, basic telescopes, and understanding techniques. And basically the bottom line is that one has to be open to theoretical ideas as well as observational techniques and not tie oneself down rigidly to some theory, because solutions may come via methods which one has not at all thought of earlier. Thank you.
For this wonderful talk, very energetic and wonderful talk.
So protons and protons.
So the students' questions? Yes.
Sir, you explained the horizon problem. Can we relate it to Minkowski's space-time diagram?
Okay. Okay, good question. Because the diagram which I drew was Minkowski. And see, the reason is, okay, its reason is a bit technical. You see, if you remember, the time axis, I did not put as t. I put as eta, which is integral dt by a. Now, what happens is, in terms of this time, this modified time variable, even in expanding universe, light cones always go in straight line, although it is not Minkowski. Okay, so it is not Minkowski, but the time coordinate has been modified in such a way so as to give a, simplified picture.
One more question.
Yes, can ask many more questions. I mean, people may be bothered about bus leaving, but that's fine.
Sir, could the concept of multiverse internal inflation be seen as crossing into metaphysics?
Yeah, I mean, okay, I'm forced to tell about my view about it. I think multiverse, saying that there is multiverse is like saying there are two gods. If God is supreme, there can be only one. Same thing with the universe. Okay, the moment you say multiverse, it's a very strange thing. I mean, if there are two rooms which are connected, you won't say there are two houses. You say one house with two rooms. So, it's like, I would say that, you say multiverse, but they're different parts of that same universe. So, I mean, I don't understand that multiverse, whatever.
Questions?
With great reluctance, he's sort of raising his hand.
सर आपने शो किया था स्लाइड में कि जब यूनिवर्स बहुत हॉट था तब लेट्स से प्रोटॉन और एंटी प्रोटॉन कंबाइन होके गामा गामा दे रहे थे। फिर यूनिवर्स कूल हुआ तो गामा पास इतनी एनर्जी नहीं थी कि रिवर्स जा सके। तो ये गामा, तो यूनिवर्स में उस हिसाब से 50% मैटर और 50% एंटी मैटर होना चाहिए।
Yes, yes, good question. Very good question. So, okay, so that is the other problem which I did not mention. So the question is, sit down, sit down. So what you are saying is, there is equal probability for, there is equal probability for matter and antimatter. So everything should annihilate and we should not be, you and me should not be there. Okay. So this goes under the thing of, what is called baryogenesis problem. Okay, you give it a name that it becomes very clear. So, why is that there is a slight extra baryons and antibaryons? Answer is easy. Okay, now there are something called the Sakharov condition, in which, if you have there are three conditions. You need thermodynamic non-equilibrium, then some CPT violation and something, then this can happen. But again, I'm not sure if there is a last word which has been said on that. Yeah.
For that to occur, there should have been a CPT violation.
Yeah.
But there are no proofs of CPT violation till now.
Sorry, CP violation, not CPT violation. CP violation. Sorry. CP violation. Yeah. Okay, and there is one more condition. I don't know if you have heard of Sakharov. Sakharov was the father of hydrogen bomb, Russian, and he also got the Nobel Prize for Peace. Okay, so that is because after he made the hydrogen bomb, he said that it's a very bad thing and so on. Okay, so and also, secondly, those days he said something against Russia, so he got the Nobel Peace Prize. Okay, so he has made this. He was a physicist, so he made these conditions, formulate these conditions, three conditions for baryogenesis. And I'm still not sure if it is sort of done.
Any more questions?
You're making the organizers more and more nervous about the bus. Okay.
So in the Biermann's battery mechanism, so it is like that
Which mechanism?
the Biermann's
Biermann battery, huh?
Yeah. So in that, I mean it's simply like that the amplification can be done due to dynamo processes of the seed magnetic field. So at what stage of this universe?
No. Biermann process seeds the magnetic field,
seeds
not evolution.
Okay. So at this seeds basically is come from the different motion of this electron and the proton.
Yeah,
so
basically it comes when the pressure gradient and the density gradient not same direction, so cross product is non-zero.
Okay, so at what stage, I mean, we can say that these seeds occur, I mean, in the universe?
These are more of at least clusters of galaxy scales.
Okay.
Yeah.
Not prior to that.
No. It's a completely astrophysical process, not a process.
Any further questions?
Sounds threatening.
So, because I want to ask my question.
Just
I used to have a question about, so what do you think, how to address the H0 tension? Because it's a 67 and 73. So
I have a,
megaparsec.
Yes. See, I am one of those more conservative physicists. And as I grow older, I become more and more conservative. So somehow I want to sort of find a solution with known physics. And I would have thought, I don't know if it's true or not, I want to do this calculation sometime. Suppose we are in till now what we think, 100 megaparsec is the scale over which the universe is homogeneous. Now I say that actually the universe is inhomogeneous or much bigger scale. So this supernova which I am seeing is actually a local phenomena. And because of the evolution of this supernova, I see it as if there is a Hubble parameter, but the actual cosmological thing is a micro background. The downside of this is the following. This would mean that if I have a spherical distribution in which it is there, it is highly unlikely that I am right in the center. If I am on one side, I will see an anisotropy in the Hubble parameter. So this is something which needs to be calculated.
Yeah. Okay. If there are no further questions, then let's thank
Thanks,
Seshadri
thanks,
again.
thanks.
And I would like to request our director to give a small memento to Professor.
Hey, how do you switch it off before you say something unparliamentary? Okay.
Yeah, basically, the advantage of a still photograph is that the information is there only of position and not velocity. So you don't know whether I'm giving it to him or not.
They would take a video, motion picture, motion photograph. Okay, so with this we sign up for today and thank you.